Dear students, in today's section we are going to discuss force on a charged particle in magnetic field. When a charged particle is placed in electric field, it experiences an electric force. We know electric field exerts force on the stationary or moving charged particle. When same charged particle is placed in magnetic field, it can also experience a force provided that certain conditions are met. That means there are certain restrictions on the charged particle for experiencing the force in the magnetic field. So let us discuss what are the conditions. There are two conditions. Condition number one, the charged particle must be moving because no magnetic force acts on a stationary charged particle. That is, magnetic field does not exert any force on the stationary charged particle, right? And second and very important condition is the velocity of the moving charge must have a component that is perpendicular to the direction of the magnetic fields. If these two conditions are met, then only we can say there is the force on the charged particle in magnetic field. So now let us discuss how to calculate this force. For finding the force, we do certain experiments by firing the charged particle through point where magnetic field is defined, using the various directions and speeds and measuring the force on the particle that is acting on that point where magnetic field is defined. Okay, so let us discuss what are the important directions where the experiments are done. First direction that is very important, when we project the charged particle parallel or anti-parallel to the magnetic field, the charged particle experiences no magnetic force. That means there is no change in the magnitude of the velocity and no change in the direction of the motion. That means magnetic field exerts no force when charged particle is moving in the direction of the magnetic field. Okay. And second experiment, if charged particle moves perpendicular to direction of the field, suppose you can follow the diagram, the magnetic field is along the positive x direction and charged particle is projected in the y direction, that is perpendicular to the magnetic field direction. And it is observed that charged particle experience the maximum possible force in this situation. That means if velocity vector and magnetic field vector perpendicular to each other, the force experienced by the charged particle is maximum. And also one very important observation are taken that force act on the charged particle perpendicular to the plane which is having the magnetic field and velocity vector. You can follow the diagram, right? One very important thing also observed, you can follow the same diagram again because you can observe the velocity and force are perpendicular. You might have learned in the mechanics section, when velocity and force are perpendicular, the path or trajectory of the particle is circular. So here we can say the charged particle, if projected in such condition, moves in the circular path, right? And here one important thing to be observed or to be noticed, in this case, force is acting perpendicular to the direction of the motion. That means the displacement vector and force vector are perpendicular. That means there is no burden by the magnetic field or magnetic force on the moving charged particle. That means the speed of the charged particle remain unchanged. So these are two important conditions. One, when charged particle is thrown in the direction of the magnetic field. Second condition, when charged particle is moving perpendicular to the magnetic field, right? Now let us generalize the case. Let us start moving the charged particle in any direction, say theta with respect to the magnetic field direction. You can follow the diagram here. What we can do, we can make the component of the velocity parallel to the magnetic field and perpendicular to the magnetic field. The component which is parallel to the magnetic field, that is v cos theta, is nothing to do with the force, because the component of the velocity which is parallel to the magnetic field will not responsible for the force. And this v sin theta is the important, because it is perpendicular to the magnetic field, it is responsible for the force. So the magnitude of the force we can say is proportional to the magnitude of the charge q naught. Greater the magnitude of the charge, greater the force. So here we can write this F is proportional to charge, that is Q naught. And as we discussed, V sin theta is the important direction. So this force is proportional to V sin theta. Correct? That is V sin theta. And also, if we increase the magnitude of the magnetic field, we find the value of the force also increases. That means the magnitude of the force is proportional to the magnetic field B. Now let us combine the result together. So let us draw this figure again. And now we can write F is equal to Q naught multiplied by V sin theta multiplied by B. This is the magnitude of the force. And here we can observe this force is perpendicular to the plane which is having the velocity vector and magnetic field vector. And theta is the angle between these two vectors, that is V vector and B vector. That means we can write this force equation in the vector form by writing F vector equal to Q naught multiplied by V cross B. So we got the equation of the force acting on the charged particle while moving in the magnetic field. Now let us learn how to find the direction of this force acting on the charged particle. So let us write this equation again. You know, this is the cross product of the velocity and magnetic field vector. And for finding the direction of the resultant in the cross product, we use right hand rule. And here also we can apply the right hand rule. If we stretch the finger of the right hand in the direction of the velocity vector and curl toward the magnetic field vector, the thumb direction will give the direction of the force acting on the charged particle, like this. Okay, and you can observe this force is perpendicular to the velocity vector and magnetic field vector. Also, the direction of this force vector is perpendicular to the plane containing the velocity and magnetic field vector. Right? There is one more rule, that is the right palm rule. This right palm rule is very easy to apply and it is also very useful rule. So let us learn the right palm rule. Suppose you stretch the finger of the right hand in the direction of the magnetic field, like this. And velocity of the charged particle is in the direction of the thumb of the right hand. So you can observe this direction, that's the palm direction, is facing the direction of the force, right? So this is the right palm rule. These two rules can be applied on the positive charged particle moving in the magnetic field for finding the direction of the force. Suppose if charged particle is not positive, it is negative. We can still use the right hand rule and right palm rule both. What we will do, we can consider the charged particle first as a positive. It may be negative. First you consider charged particle is negative. And apply the same rule, that is the right hand and right palm rule, and find the direction. And finally, you should reverse the direction of the force. That direction gives the direction of the force acting on the negative charge. So we got the magnitude of the force, we got the direction of the force, and we also learned the rules governing the direction of the force. So let us apply these concepts through one illustration. You can observe here this illustration, a charged particle is projected in a magnetic field. We are given the magnetic field vector B equal to 2i cap plus 4j cap into 10 to the power minus 2 Tesla, right? And acceleration of the particle is found to be a vector equal to xi cap plus 2j cap meter per second. And here we are asked to find the value of x. X is unknown at this equation. Okay. Now, we know force acting on the charged particle, that is equal to F equal to Q naught V cross B. And we have discussed here, this force is perpendicular to the plane containing velocity vector and magnetic field vector. Now we can write F should be perpendicular to the magnetic field vector, right? And we know the direction of the acceleration and direction of the force should be same. That means the acceleration vector should also be perpendicular to the magnetic field vector, right? Now, if acceleration vector and magnetic field vector is perpendicular, that means the dot product of the acceleration vector and magnetic field vector should be 0. So we can write A dot B equal to 0, and acceleration of the particle is xi cap plus 2j cap, and magnetic field is 2i cap plus 4j cap. So dot product of these two vectors should be 0. If we do the dot product, that is equal to 2x plus 8 equal to 0. That means x equal to -4, that is -4 meter per second square.